All right, good morning. I know I'm between you and a tea break, so I'll try to get this going. Thanks for the introduction. I'm Jacob Torrey. I am a senior security researcher at a small company called AIS. I work with a very low-level group there that works at the hardware, software, and firmware levels, mostly on Intel platforms, which I'm guessing you're all running somewhere in your organization. So my thesis, before I get down to the nitty-gritty, is that modern hardware is supporting so many optimizations to get the last amount of performance out that it's creating software-level security challenges that face your organization that kind of are stemmed and rooted in the hardware. And because of this, they hamper your abilities to detect and prevent compromises and breaches in your network. And so I'm just going to give one example. This is the work I did. Actually, it was funded by DARPA, and showing how this kind of performance enhancements at the hardware level can actually have kind of a ripple effect and unintended consequences when it comes to preventing a software-based attack. So jumping right in, a little bit of background here. So the Intel X86 platform, which is running your standard Windows, most Linux servers, anything with an Intel inside or an AMD processor, provides the capability in the CPU for operating systems to kind of abstract and manage memory in a method using what's called paging or virtual memory. And so this prevents one application from, say, accessing memory in another application, or even worse, back in the days of DOS, an application that was misbehaving could actually overwrite the operating system and inject a rootkit directly into the operating system. And so essentially what you have is you have a virtual address and then you have a physical address. And the operating system kind of controls these by using a set of page tables. And so when the CPU goes to look up and figure out what the physical address to ask the RAM for based on your virtual address, it goes through and it asks for the page directory entry, and then the memory brings that table into the CPU cache, and then it asks for the page table entry, and then it goes and actually gets the memory. And this is very, very slow. So as you know, memory is probably the biggest bottleneck in most modern CPU-based applications. I was reading some research that shows about 50% of performance hit is because of the bottleneck from memory. And so to be able to kind of bypass this concern with security or with the performance, CPU vendors, they added what's known as a TLB, a translation Lookaside buffer. And that is essentially is just a very simple CPU cache that after you've gone through this lengthy process, you can save the mapping. And then next time you need that mapping, it's already there, it's much faster. And so this is accounts for about 50% of performance hit. It is when you have to go and re-walk all those tables. So the example I provided in this thing shows 3 memory accesses for accessing one amount of 1 byte or 1 page of memory. This is a very simplified example. If you were running something like a cloud environment and you're running in a hypervisor, it could be upwards of 7 to 9 translations. So if you want to read 1 byte of memory in your application, you're going to have to go to memory at 7 or 8 different places before you can actually get that one byte of memory. And so the performance impact of this can be pretty immense. So that's where this TLB came from. And so logically, it just stores a virtual to physical address mapping. Where it gets very, very interesting is when the chip manufacturers laid out the TLBs, they actually split it up into 2 TLBs. There's an instruction TLB, which saves mappings for instruction lookup, so when your code is going to execute, when it asks the memory, hey, load this program into memory, it's going to use the instruction TLB. And then there's also a data TLB, which is for data references. And so 100% of the time during normal operation, they're completely in sync. And so they both point to the same memory address. This is what's known as a von Neumann system, where you have a shared view of memory depending on whether you're looking for instructions or you're looking for data. So unfortunately, now that that's kind of been identified as not being actually the case, there's been some attacks. So Shadow Walker was a rootkit that actually desynchronized so that the data TLB and the instruction TLB pointed to different regions. And this was used kind of a variety of different ways in the past. So Shadow Walker, really interesting, what it did is it would provide a rootkit into a Windows kernel image. And it would show in the data TLB the unmodified kernel. So when you were running your antivirus or your anti-rootkit software or any type of other host-based protection, and it would look at the kernel to make sure that your operating system hadn't been compromised by an APT-like threat, it was going to see the unmodified. However, when the operating system was actually scheduled or responding to a request from an application, it would go through the ITLB and load a separate set of region of memory which was compromised. And so this right here shows that now you can't even trust reading memory to do your own verification. Because of this hardware level difference and these optimizations that were performed at the hardware level, you now have software level threats that are impacting your organization. Just a real quick picture highlighted in red, you'll see that there's a different TLB for instructions and data. So this kind of I've already mentioned briefly, but just differences in perceived hardware versus actual hardware. So, and just because something runs how you expect it to do, say 100% of the time in your test cases, doesn't mean a dedicated attacker could be able to kind of change how those assumptions actually work, because unless you're looking at how the hardware is working in reality, you might be making some assumptions that hold for, say, 90% of the cases, but it's the attackers that are going to find that 10% and be able to penetrate into your organization. So once the Nehalem or the Core I, Core i3, Core i5, Core i7 CPUs came out, they actually added a second level TLB again for performance reasons, but another unintended consequences of this is that it actually broke TLB splitting. So if you were running a Core I series processor, you were not vulnerable to these threats. And so you'll see right here, now in red, is the STLB, which has bidirectional arrows that kind of go between the instruction and the data TLB. So now the hardware is implemented, how it's actually used. And so now you have 100% of the time you are you're accessing data and instructions in the same method. And so now you have a full von Neumann machine model. So that was the end of the story until I got my grant. So we had a project called MORE, which is running of executables. So we thought we could use this technique to automatically separate code and data. So when an application is originally run, if you're doing trusted computing and your trusted launch, you can measure that region of memory or that binary and hash it with, say, a SHA-1 or SHA-256 hash, and be able to determine, okay, is this the same hash that I was seeing yesterday or what I saw from the vendor, or someone perhaps injected malicious code in there. However, as that program starts running, the variables are going to start changing. So if you're hashing that region of memory, the hash will change. You're not sure if that's because the variables have changed or because the code has been compromised. And so we were wondering if we could take an existing binary and an existing program that was already compiled down to a .exe and be able to use this TLB splitting for a defensive purpose. Could we split out automatically the executable from the data? And so that was a program under Cyber Fast Track. The pretty well-known hacker Mudge was actually the program manager for that. And so here we were actually able to ask the question, has this unknown binary been modified maliciously, or is it still operating how it should? So what we did is we actually built a custom thin hypervisor that allows us to monitor processes so we could target specific applications that were of vital importance. So antivirus, we wanted to make sure was not getting compromised. Any other kind of host-based protections that we wanted to make sure, logging frameworks, audit frameworks that we wanted to protect. We could say, okay, these are the list of applications we care about. And then actually we found a way to re-break this and re-get TLB splitting to work. And so some of the new virtualization capabilities found a way around the shared TLB, and we were able to break this model once again and kind of bring back all the security threats, but also for the benefits of TLB splitting. So our results, so I wrote this hypervisor in about 2 or 3 months, and even with that prototype nature, we were seeing less than 2% performance hit and being able to measure an application that was dynamically changing and determine its trust status less than 1/10 of a second. So we were getting pretty close to real-time analysis of